Today we will go over section 15.2. 15.2 is on iterated integral. In fact, I think we're supposed to have that double integral on rectangles. The one we have, that's the title in 15.1, right? Double integrals over rectangle. That's supposed to be the title for this 15.2. Okay, now 15.2, they say it's iterated integral. Basically, it means you have integral nested inside an integral. Okay, let's start with some theory. Suppose fx is continuous on domain R. This R here stands for rectangle. AB by CD. So imagine if we have a domain R. Let's say this is the x-axis, this is the y-axis, and then this is our domain of integration, where this is A to B by C to D. Okay, in 3-dimension, let's say it looks like this. Now, please, if you can, please follow me in drawing though. Yeah, please follow me in drawing, if you can. So in 3-dimension, let's say the domain is like this. This is the domain, where this is A to B, and this is C to D. So this is our R here. Okay, now, and we want to integrate over a function. Let me use what color? Maybe I use green color. Okay, over a function, a surface on the top of this R. Okay, let me color that with maybe a very light green. Okay, so this is the surface here. Now we usually call that surface S. Okay, so S is the surface, and the shadow of that surface on the ground, because it looks like rectangle, we call that R. Now, so that's the situation. Okay, and this function is continuous. Basically, the function is predictable. Okay, now let's go back to the storyline. Now, then let AX be the partial integral. Remember the partial derivative? Now this time is partial integral. Partial integral with respect to y. What is that? What is that? So what happened is we choose an x between a and b. We choose an x between a and b. Let's say this one here. Let's say this x here. Okay. Let's say this x here. Okay. In our 3D, let's say that's the x here. This is the x here. Okay. Now, that will be that ax will be the integral between C to D, from C to D of that function fxy dy. Now, this can be seen as the area, quote unquote area, associated with cross section at X. So if you take this cross section here, you take it out, then it looks like this. So it looks like this. It's from C to D, and this is the Y. This is the C. Okay, this curve on the top here is the cross section fxy with x fixed. Okay, now this is the area that depends on x. Now notice that because the area that depends on x depends on the cross section of x, then when we integrate this, x is considered constant. X is considered constant. Constant. Just like when we do the partial derivatives, right? When we do partial derivative with respect to y, then we consider x as a constant. Right now, when we do integration with respect to y, x also is considered constant. Okay, x is considered constant. Maybe if I emphasize because it is an integral with respect to y. Okay. Now, if we go on further, the volume, quote unquote, the volume, I use quote unquote here because that's actually only true if the function fx and y is non-negative. Okay, now is therefore the summation of all areas of that cross section respect to x. Okay, if you remember, I think in chapter 5, the way you guys compute the volume of revolution, you basically do the disk method, right? Okay, you compute the area of the disk or the volume of that little disk, and then you add all those little disks to get the volume of the solid, right? So I think you at that time you get this one, right? What is that? So suppose this is fx. You revolve that with respect to x-axis, then the area there will be pi fx squared, right? Okay, multiplied by the dx, that's the thickness, and you integrate with respect from a to b. Okay, I think that's the way we did it, right, at that time. Okay, now what happened if the volume is not a disk? It's like a more general case. Well, basically we still use that notion. Okay, we still use that notion. So we find the area of the cross section. In this case, we call that AX, the area of the cross section at X, and then which is this guy, the area of the cross section, and then after that we add the area of those cross sections to get us the volume. Okay, therefore we now see the following integral. If we replace that, we substitute that ax back, we will see a integral a to b integral of c to d of f x y dy dx. Okay, now of course similarly integral from c to d, integral from a to b of f x y dx dy. Notice I reverse the order of integration. Earlier I integrate with respect to y first, and this domain, this interval here is the domain for interval in y's, right? And then after that I integrate with respect to x, and the AB here is the interval for x, right? Now this last integral that we have, we integrate with respect to x first, where the a and b in the limits of the integrations is the interval, the endpoints of interval of x, and then after that we integrate with respect to y. Okay, so what we did there basically, is basically integral from c to d of area as a function of y, and we integrate with respect to y. Okay, where the area with respect to y is actually integral from a to b of f x y dx. Okay, now that's the idea. Now let's practice with some integrations. And of course, at this point, I need you to be quite strong with your integration from Calculus 1 and Calculus 2. That's why Calculus 2 becomes the prerequisite for this class, especially for this section here, for this part here. Integral from 0 to 3, integral from 1 to 4 of x squared plus y cubed dy dx. What does it mean? Well, it means we will integrate with respect to y first. Okay, now I do not want you to detach the integration. Some people, they like to do the single variable integral first, and then after that they've done with this red integral, and then they integral with respect to dx. No, don't do it that way. Don't do it this way, that way. Okay, now, but Thomas, I get the same answer. It's not only about the same answer or not, it's about the technique, the way you show the work. Okay, if we use equal sign here, then keep it equal, right? You don't do only inside. So then when I integrate the guy inside with respect to y, then I will get x squared y. Remember, x is a constant, right? So x squared integrate with respect to y give us x squared y plus, now y cubed. When you integrate it, we get 1/4 y to the 4th. Okay, from 1 to 4 dx. Now then we will compute that inside the integral. Okay, so that will give me the y will be 4. 4 to the 4 divided by 4, that's 4 cubed, that's 64, minus y is 1, that's x squared plus 1/4. Right? And then from there, let's combine like terms first. So this becomes integral from 0 to 3 of 3x squared plus 64 and 3/4. I'm sorry, 63 and 3/4. What am I doing? Subtract my 1/4, right? 63 and 1/4 dx, which when I integrate with respect to x, give me x cubed plus 63. No, that's not 1/4, that's 3/4. 63.75x from 0 to 3. Right? Which is equal to 3 cube is 27. That's 27 plus 63.75 times 3 minus 0 plus 0. It's 27 plus, what's that, 180, whatever it is. I'm so lazy to compute it. So this is 191.25. What is this? So that is 218.25. You don't need me to do this for you. You don't need me to do this for you. Now, the thing is, if the domain of the integration, if the domain of integration is a rectangle, like in this case, if you see the domain is, the x is from 0 to 3, the y is 1 to 4, right? Okay, which is a rectangle. And second, if the function also continues, you see it's polynomial, so it's continuous everywhere, right? And oops, and fxy is continuous in that domain, then we can interchange the order of integration. In other words, our example 1 can also be done this way: integral from 1 to 4, integral from 0 to 3 of x squared plus y cubed dx dy. Okay, and that's supposed to give us the same result. That will give us 1/3 x cubed plus xy cubed from 0 to 3 dy. When I plug in x equals to 3, I will get 9, and then 3y cubed dy, and then when I integrate that, I get 9y plus 3/4 y to the 4th from 1 to 4. That will give us 36 plus, what's that, 3 times 64 minus 9 plus 3/4, right? 36 minus 9, that's 27. 64 times 3 minus 3/4 is 64 times 3 is what? 192 minus 3/4. 191.5. Oh, I get the right answer earlier. Surprise. That's equals to 218.25. Okay, but The rules is, the one you need to remember is only if the domain is a rectangle and the function over that domain is continuous. Okay, that brings us to a theorem called Fubini theorem. Okay, Fubini theorem says if a function is continuous on the rectangle, okay, this is our textbook way to write that rectangle. My way of writing that rectangle is AB integral AB by CD. So the first interval for x, the second interval for y. Okay, then this integral will be the same even if you reverse the order of integration. Of course, when you reverse the order of integration, the y still with the y's. Okay, the y still with the y's. The x still with the x. Okay. We call that Fubini's theorem. You can say this Fubini's here is basically kind of, not exactly the same idea with Clairaut's theorem, but Clairaut's theorem was for derivative, the higher derivative, right? The second derivative, second mixed derivative. Clairaut's theorem says that f sub xy equals to f sub yx if the function, the first derivative of the function is continuous, right? Okay, in a small neighborhood, in the neighborhood of a coordinate, which is not in the boundary. Now, Fubini's theorems only requires that to be continuous. In fact, Fubini's theorems actually is more general. It only requires the function to be bounded on that rectangle, maybe discontinuous on some points or some curves, right? As long as the iterated integrals exist. If it satisfies these situations, which ideal situation will be a continuous function, then we can reverse the order of integration. Now, don't forget this though, don't forget this. I'm basically telling you one new technique of integration. Technique of integration is reverse the order of integration. Now you will see this technique of reversing order of integrations will show up again in future under some situations, but in the most ideal situation, if the domain is a rectangle. Okay, if the domain is rectangle and the function is continuous over that domain, then we can integrate it in two different ways and we'll get the same answers. Now, integrating it with two different ways does not imply both of them will be easy. No, it is possible one of them hard, therefore we prefer to do another way. I think when you look back to this example here, I think the second method is easier, right? I think the second method is easier. Now, how do we know in advance that the first method or the second method will be easier? To be honest with you, I don't know. Even if I don't even if I know it, I will not tell you because that's something you're supposed to learn and gain through examples, okay, through exercise. I can tell you that thing right now, but then in some cases it doesn't work. Okay, I can tell you now, like in this example here, why the second way of integrating is easier. Well, because the second way of integrating, you have that zero, right? When you integrate and you plug in zero, it will kill all the terms, right? So when I replace the x dx here by 3, I get this part. But when I replace the x here by 0, it just disappear, right? Okay, that's the reason. That's the reason. But of course, it's not true in general case. For polynomial, we like to have 0. We like to have 1 also. Okay. Now let's do some example, and I want to say that Yeah, let's do some example first. I pick question from our textbook. Let's say I do number 6 in our textbook. Yeah, this number 6. We integrate first with respect to x. Oh, but the function has no x, huh? So what happens if you integrate a constant? I want to say this. In Calc 1, suppose I have integral from a to b dx, which is basically the case we have right now. I want you to realize this is equal to integral, when you integrate 1, that gives you x from a to b, but that's basically b minus a, right? In other words, if you integrate a constant, that gives you the area of a rectangle with height equals to that constant, and the length is the length of that interval. Okay, suppose I put a c here. Okay, this will be cx, and this will be c times b minus a. Okay, if you think about it, let's say this is the constant c, that's the height, and this is a, this is b. That integral will give you the area of this rectangle, right? Okay, now why I tell you this, so that you don't need to do some meaningless integrations that we can easily do mentally. Okay, again, you're in Calc 3, so there are things I do expect you to skip. Like for example, here when I integrate with respect to x of cosine y, that will give me cosine y, because that's independent of x, times the length of that interval, 5 minus -1, right? I don't even need to show, oh, that is equals to. You can, but why? You can say, oh, this is actually cosine y times x from -1 to 5 dy. This is equals to pi over 6 to pi over 2. And then cosine y times 5 minus -1. See, the thing is, like, for more difficult stuff, sometimes you skip steps, but for this simple stuff, you want to show work. I wonder why. Please don't do this, okay? If you can skip that, please skip that. So then we come up with this. We can pull the 6 out, and we basically just integrate cosine y from pi over 6 to pi over 2. Respect to y, that gives us cosine, oh no, not cosine, sine. Integral of cosine is sine y from pi over 6 to pi over 2. That will be 6 times sine pi over 6 is 1. I'm sorry, sine pi over 2 is 1. Sine pi over 6 is 1/2. So this is equal to 6 times 1/2, which is 3. Okay. Now that's for example number 6. Now we happen to touch base one important other technique of integration. Unfortunately, this technique only applies if you have rectangle. What technique is that? When the integrand, if the integrand fxy is separable into the function of x only times the function of h only on R, which is a rectangle, okay, then we can actually rewrite that integral now into the product of two integrals. We can rewrite that double integrals into product of two integrals, two single variable integrals. If we look back to that number 6, so you see integral from pi over 6 to pi over 2, integral from -1 to 5 of cosine y dx dy. Notice that this is basically cosine y times 1, right? Which I can rewrite as integral from pi over 6 to pi over 2 of cosine y dy times integral from -1 to 5 of 1 dx. Of course, we can just omit that 1, right? And this will give us sine y from pi over 6 to pi over 2, and this is equals to 6, right? So this is 6 times 1 minus 1/2, that's 3. Now, but life is not always this clean, this nice though, okay? It's not always this nice. It's never wrong to do maybe one more problem. The problem that has something to do with that, I pick number 8. Number 8. Let me do it here. Okay. Now notice that the domain of integration is a rectangle, right? In fact, it is from 1 to 3 for the x, and the y is from 1 to 5. Okay. Now the function is separable. Ln natural log of y over xy can be rewritten as 1 over x times natural log of y over y, right? So because of that, I can separate this iterated integral into the product of two single variable integrals from 1 to 3 of 1 over x dx times integral from 1 to 5 of natural log of y over y dy. Okay, now integral of 1 over x is natural log of x, absolute of x from 1 to 3, is it right? Times, the second part is a bit tricky. How do I do this? How do I do that? How do I integrate natural log of y over y? Let's do u substitution. Let u equals to natural log of y. Then du will be 1 over y dy, right? Okay, so u1 is ln 1, which is 0. u5 will be natural log of 5. So this integral now becomes integral from 0 to natural log of 5 of u du, right? Okay. Notice I don't want you to do you to detach that integral. Okay, if not necessary, don't detach them. Okay, this becomes natural log of 3 minus natural log of 1, which is 0, times, this is 1/2 u squared, 0 to natural log of 5. So this is natural log of 3 times 1/2 natural log of 5 squared. Okay, I think we can simplify this and call this, no, I cannot. I thought I could, but I cannot. This is natural log of 5 squared times natural log of 3 over 2. Okay, but you see that once we identify that the domain is a rectangle and the integrand is separable, then we can do this business. Okay, the idea is basically as follows though. If I try to prove this theorem here, it's basically like this: integral from a to b, c to d of f x y, which is separable, so it becomes gx hy dy dx. Now, notice that because gx is independent of y, then I can move it out. Integral from a to b of gx, integral of c to d of hy dy dx. You see that? Right? Because gx is independent of y, the whole function is basically a constant relative to y's. But then, when you integrate this will give you a number. Let's call that number number k. Okay, so we now have integral from a to b gx times k dx, right? But because that's a constant or coefficient, we can pull that k out. Is it right? Now that k is coming from integral from c to d hy dy. I hope that becomes clear for you why we can rewrite that double integral over rectangular domain into the product of two single variable integrals, one respect to x, the other one respect to y. Only if the domain is a rectangle and the function is a separable function. Okay, if one day you take differential equations, the word separable function becomes something you need to know again. Okay, that enables us to do some integration that may seems to be difficult, turns out to be a simple one. Okay, but again, life is not that nice all the time. Okay, let's say for example, I pick question number which one? Number 12. Yeah. What happened here, the domain is still a rectangle, which is nice, and we love that. But the integrand not separable because of this guy here. This guy here, we cannot separate that. Okay. You know that, right? You're in Calc 2, you know that square root of a plus b is not equals to square root of a plus square root of b. Okay, I hope you are clear with that. If you don't believe me, just use 1. Square root of 2 is not the same to square root of 1 plus square root of 1. Okay, that's clear, right? Square root of 2 is not 2. Well, anyway, this is not the appropriate level for me to talk about that. You're supposed to know it. But when we integrate this, let's see. It seems like the integration is, I integrated with respect to y first. Okay, so let's do u substitution. Okay, let u equals to x squared plus y squared. Then du respect to y will be 2y dy. Right? Okay, or you can say y dy is du over 2. Okay, notice that this guy is my du over 2. Okay, now what happened when y equals to 0? When y equals to 0, I get x squared. When y equals to 1, I get x squared plus 1. In other words, my integral now becomes integral from 0 to 1 for my dx. But as for my dy, I get x squared to x squared plus 1 x square root of u du over 2. Okay, notice that this guy becomes my square root of u, right? And this guy becomes my du over 2. Okay? Remember, once you do substitution, this is a very common mistake. And some instructors okay with that. I am not okay. I'm not okay with that. What is the one you say not okay? Once you substitute to u, the y in terms of u, then you should not use y anymore in your integrations. Okay? Once you substitute that person with something else, you don't go back to that person. Okay? Just like when you break up with somebody, right? If you break up with somebody, you break up with your ex, you break up, you substitute, right? You don't go back to your ex. Okay, it's done. It's your past. Don't need to look back. Okay, now when I integrate this, oh, the coefficient 1/2, let me just pull that all the way out to the very front. Okay, u to the power of 1/2. When I integrate that, I will get 2/3 u to the power of 3/2, right? From x squared to x squared plus 1 dx. Now I plug that in. I can pull the 2/3 out, becomes with 1/2 becomes 1/3. Integral from 0 to 1 of x times x squared plus 1 to the power of 3/2 minus x squared to the power of 3/2. Is that right? Okay, so this becomes in 1/3 times, let me pull this integral from 0 to 1 of x times x squared plus 1 to the power of 3/2 minus, this is x cubed times x, that's x to the 4th dx, right? Let me just separate them first. Integral 1/3 integral from 0 to 1 of x times x squared plus 1 to the power of 3/2 dx minus 1/3 integral from 0 to 1 of x to the 4th dx. Can you follow me? Okay, now then the first integration here, I don't think you want to use strict substitution. You can if you want to, but why do you want to work so hard? We can use another substitution. Let's say w equals to x squared plus 1. So dw equals to 2x dx, right? And the w at 0 is 1, w at 1 is 2. Okay, in other words, the first integral becomes 1/3 integral from 1 to 2 of w to the 3/2 dw over 2, right? Do you see the technique again? X dx is dw over 2. X dx is dw over 2. Okay? And then that's the first part. And the second part will be the easy integral minus 1/3 times 1/5 x to the 5th from 0 to 1, which is 1 over 15. So this is 1 over 6 times 2 over 5 w to the 5/2 from 1 to 2 minus 1 over 15 from 1 minus 0 is just 1 over 15. This will give us 1 over 15 also, but that's 2 to the 5/2 minus 1 minus 1 over 15. Okay, so this will be what? This will be, I can factor 1 over 15 out. 2 to the power of 5/2 is 4 radical 2 minus 2. I think I can factor another 2 out. Let me do it. So I get 2 over 15, 2 radical 2 minus 1. Okay, now through I think I need to emphasize that what I did here is especially just to show you how to do iterated integral. Okay, notice do not detach them. Okay, keep them as one package as much as you can. Okay, but in between, you see that I basically review a little bit again about your calculus 1, right? Or you can say calculus 2, but I think you just need calculus 1 here actually. Okay, I do u substitution. Notice that when I substitute the u and I do the derivative differential with respect to y, you basically see your x as constant. Okay, so this is an example where the integrand is not separable, even though the domain is a rectangle. Now let's see one more problem. Maybe this one here, number 20 or number 21. I tend to say number 20 because that's an even number, right? Odd numbers, you have the solution at the back, right? Okay. Yeah, what happened here in number 20 and 21, the integral, they don't tell us which one first. And actually, because the domain is a rectangle, then you decide which order of integration you want to do. But sometimes then, because you have that choice, you have those choices, then you need to be wise in deciding which one to do first. Now, idea. How will you integrate that first? I think if I integrate that, I will use u substitution 1 plus xy, okay? And then I will do differential with respect to y such that I get x dy, okay? Notice that I have the x on the top, right? Let's do that then. In other words, my first integration will be with respect to y first, okay? 0 to 1 for the x, 0 to 1 for the y, x over 1 plus xy dy dx, right? And then using u equals to 1 plus xy du equals to x dy by substitution. Oh, what is u0? u0 is when x and when y equals to 0, that's 1. When y equals to 1, that's 1 plus x, right? So my integral now, integral from 0 to 1, integral from 1 to x plus 1 of x dy, that becomes du, 1 plus xy, that's u dx, right? So that's integral from 0 to 1. Integral of du over u is natural log of absolute u from 1 to x plus 1 dx. You will see this is integral from 0 to 1 of natural log of x plus 1 minus natural log of 1, which is 0. Okay, this is 0. Now then the next question is then, how do we integrate natural log of x plus 1? Now this is not 1 over x plus 1, you know. The integral of 1 over x plus 1 dx is natural log of absolute x plus 1 plus constant. That's true. Okay, but the integral of natural log is not 1 over. Don't forget the ordering. Okay, I hope you remember for this we do integration by parts. Okay, when you do integration by parts in my class, you have to do it in one of two different ways. The first one, a regular method. The regular method, you need to show me the u d phi phi du thingy, because I already used my u above. Let me call that u1 right now. u1 equals to natural log of x plus 1, and my d phi is dx So du1 equals to 1 over x plus 1 dx, and phi equals to x. This is the regular method. Okay, so this is x natural log of x plus 1 from 0 to 1 minus integral from 0 to 1 of x over x plus 1 dx. That's the first method. The second method, if you happen to know tabular method, you can use tabular method, but you still need to show me the table. Okay, the tabular method. Now, if you wonder about tabular method, you can ask me. I can show you my lecture videos about tabular method for integration by parts from my calculus 2. Well, anyway, you pass calculus 2, so you know integration by parts at least, right? The regular way. Now, integration by parts by tabular method will be very useful if you take differential equations. Of course, in general, you know, if you want to learn that, I strongly suggest you to find out. Contact me, and then I give you the lecture videos where I cover integration by parts using tabular method. Well, anyway, how do I do this? When x equals to 1, then I will get ln 2. When x equals to 0, that's 0 minus integral from 0 to 1. Let me massage it this way. I supposed to divide because this is improper fraction, right? Okay, remember when you do partial fraction decomposition, when you have rational function as your integrand, it's supposed to be in proper fraction, not in an improper fractions. What I do here, I will do this kind of manipulation, plus 1 minus 1. Okay, so I have integral from 0 to 1 of x plus 1 over x plus 1 dx plus integral from 0 to 1 of 1 over x plus 1 dx. Okay, but this is just integral from 0 to 1 of 1 dx. That will be 1 later on, and this is integral natural log of absolute x plus 1 from 0 to 1. Okay, natural of 2 minus 1 plus ln 2. So this is 2 natural log of 2 minus 1. Notice that if we choose another ordering, if you try to integrate from 0 to 1, 0 to 1 of x over 1 plus xy dx dy, I don't think this is doable. Not that I know. Not that I know. Okay, the first step is not doable. I cannot think of a way to integrate that. Okay. In other words, that's why I look back. Remember that reversing order of our integration for this Fubini theorem. Okay, give us two different ways of integrating. Okay, sometimes one of them is easier than the other. Okay, for number 20, if you happen to use dx dy, you will get stuck there forever. Okay, it's not doable. Okay, that's for number 20. Let me see more if there's other thing I can do similar to that one. Let me randomly pick a question that I don't know if it is doable with what I teach you today. Number 30. Find a solid in the first octant bounded by the cylinder z equals to 16 minus y squared and the plane y equals to 5. Z equals to 16 minus x squared. That's a parabola, right? That's a parabola. and we just need in the first octant, right? It's a parabola. It's a cylinder with cross section of parabola. Okay, with this is y equals to 5. Okay, but the surface here S is given by c equals to 16 minus x squared. Oh, what is the y then? What is the x then here? Okay, so when c equals to 0, when you set that equals to 0, we get x equals to plus minus 4. But we just need the first octant. First octant. So x equals to 4. Now our domain of integration becomes our x will be from 0 to 4 and the y will be from 0 to 5. Right? That's the domain of integration. Okay, so the volume is equals to integral from 0 to 4 for the x, 0 to 5 for the y, square root of, I'm sorry, no square root, my bad, of 16 minus x squared dy dx. Okay. But the integrand seems to be independent of y, huh? Right? It's independent of y, so that will be just, and in fact, in the integrand, there's no y at all. So when I integrate this, that will be just the length of the interval 5, right? Is that right? Okay, I can pull that 5 out and then now integrate. I get 16x minus 1/3 x cubed from 0 to 4. 5 times 64 minus 64 over 3 minus 0. What will that be? That's 5 times, that's 2/3 of 64. Is that right? Imagine if I factor the 64, I end up with 1 minus 1/3. Okay, so we get what? That's 5 times 2, that's 10 times 64, that's 640 over 3. So that's 31 and 3,313 and 1/3. Okay, that's for this one. This section is supposed to be a lot shorter than this though. I'm sorry. This seems to be, I try to explain the ideas more, but I guess I kind of carried out. Suggested homework from this section 15.2. Please practice, okay? From number 3 to 31 and 35 to 38. Right now it's 5:36. Let's take a break. Okay, let's start again. We will now go on with section 15.3. That's double integrals over general region. Now to differentiate general region and rectangle, we will call general region now a D. And you will see the focus, the first focus of our work today is basically on how to set up the integral. Okay, how to set up the integral. I would like to go over how to set up these double integrals and hopefully in future triple integrals, doing the following, going backward, long way backward. Long time ago, we want to find the length of an interval. Let's say the length from interval from A to B. The way we compute that, of course, we just subtract. The length is B minus A, right? I think that's simple. Okay, now the idea that I want to instill in you as a tool of my teaching right now is the idea of augmentation. In other words, we develop that, we see this case here in one dimension higher. You will see that the length of this interval is actually the same to the area of the rectangle if I make it the height is 1. Okay, so the length of this interval is now equals to the area of the rectangle, which is 1 times B minus A, right? Okay. We know they are the same, but the difference is the point of view. The one on the left hand side is one-dimensional point of view. It's just the length. The one on the right hand side is the area of the rectangle. They will give us the same numerical result, but one of them one dimension, the other one is two-dimensional. Of course, if I ever ask you a question, what is the length of an interval, you never use the method on the right hand side. Please don't. Okay, please don't. Just use the simple one, the one on the left. Now, my reason of showing you this is the following. Suppose what if the height varies? In other words, y is not 1 anymore, but y is now a function of x, depends on the x. Then we do integration, right? So we end up with, let me change the color first. We end up with, let's say this is a and b, right? But we have a function okay, this is y equals to fx. Now the area is equal to the integral from a to b of fx dx, right? Therefore, we end up with calculus 1, remember? So we start with the length, okay? If the density of every point on this line segment is uniform, is 1, then this length here is the same to the area of the rectangle with length 1. If the density is uniform with density, let's call that k, then the weight of that line segment there will be equals to the area with height k, the area of the rectangle with height k. Now, suppose I change, instead of the height to be constant k or the height equals to constant 1, let's say the height now varies as a function of x. Then the area now can be represented by this integral. Okay? Now notice that we start from 1 dimension to 2 dimension with height 1. Now we varies the height, becomes a function of x. We now compute that using integral. right? Okay. We can also compute this using integral if you want to, but nobody should. No, you should not integrate this integral from a to b of 1 dx, even though you can do that, right? You can do that. That's the same. It gives you the same area, but no, nobody will do it, right? Okay, nobody will do it that way. But you see how we actually move from one dimension to rectangle, now becomes two-dimension integration, the integral over the segment AB with height 1. Now, I want to do the next augmentation. This time, I want to see this area in the following way. Suppose I have, this is my A and this is my B. Okay, that's the area, right? Of that. Now, I do augmentation with height 1 right now. Let's say z equals to 1. So that area that we have is now the same to the volume of prism with domain equals to the region R. No, don't use R, D. You see the base now is a D, do it domain D, and height 1. Right? Notice how I move from a two-dimensional notion area to the three-dimensional notion volume. Okay, but this volume now, if we express that as a double integral, it will be integral from A to B, integral from 0 to 1 of fx dy dx. I'm sorry. Yeah, is it right? Mm-hmm. Notice that I can go on further. I can go on further and make it as follows. This is integral from A to B. Integral from 0 to fx dy dx. Is it right? And notice that you can say the height 1 is here. This is the height 1. And notice that this double integral here represent the region D. Okay, so what I want to really, the point I really try to make is, so if we have domain D, domain of integration D, with integrand fxy, in which we replace the 1 by z fxy, then the integral will look like double integral over d of fxy dA. Okay, now to be more precise, with the double integral d, we rewrite the area of d in double integrals. Okay, now let's do example. Okay, so far I give you the technique, right? I give you the notion, but let's do an example. Suppose I do example 1 from our textbook. You will see I actually go over examples from our textbooks. Okay, because you will see it's more about practice though. Okay, suppose we have double integral over domain D. So that's our issue. Now we have the integrand. This is our integrand c equals to fxy. Okay, where D is region bounded by parabolas y equals to x squared and y equals to 2x squared and y equals to 1 plus x squared. Okay, now of course you are in Calc 3. I do expect you to know what each of these curves look like. Okay, so suppose I think you know 1 plus x squared. 1 plus x squared is the regular parabola with vertex at 0, 1. It looks like this, and it is symmetric with respect to y-axis, right? And then 2y squared, the vertex is 0, 0, but it's sharper. It increases faster. Okay, eventually they will intersect. The problem is, where do they intersect? Then how do we find that? Where do they intersect? We set them equal to each other. So the y equals to the y, 2x squared equals to 1 plus x squared. So x squared equals to 1. So x equals to plus minus 1. So we know this is -1 and this is +1. Okay. Now then go back to your calculus 1. How do you rewrite the area of this region D using single integral? Let me use a light color for now. Okay, the area is equals to integral from -1 to 1 of the curve on the top, 1 plus x squared, minus the curve at the bottom, 2x squared, right? dx. Okay, that's the area of the domain D using single integral. Now rewrite this as double integral. As a double integral, then it becomes integral -1 to 1 of 4 dx, integral from 2x squared to 1 plus x squared for the dy. If I put 1 here, that will give us the prism with height 1, the volume of the prism with height 1. Okay, but now they tell us the integrand is not 1. Okay, the integrand is not 1. The integrand instead is x plus 2y. Now, my point is, how do you set up the integral? That integral comes from, you do this finding the area. Okay? So the double integral that we need to compute in this example, double integral over d of x plus 2y dy dx. Okay, how to find that d? Think of that. Imagine if you try to find the area using single integral, it will be something minus something, right? Okay, now that something minus something, you break it into integral. Okay, maybe I mark it this way. This guy here becomes this guy. Okay, but once you are done with that integral, setting up the integrals, everything from here is just computation. Okay, so we will integrate with respect to y first, then I will get xy plus y squared from 2x squared to 1 plus x squared dx. Substitute. So this will be x times 1 plus x squared plus 1 plus x squared squared, right? That's the first term. Minus x times 2x squared plus 2x squared being squared dx. Is it okay? Everything from here is algebra. Everything from here is algebra. But let me work it out. Let me work it out. Because you will see some fun stuff. Okay. For example, if I break it up, here I get x plus x cubed plus 1 plus 2x squared plus x to the 4th minus 2x cubed plus 4x to the 4th dx. Is it right? Okay, go on further. Integral from -1 to 1 of, when I combine them, what do I get? I get negative 3x to the 4th minus x cubed plus 2x squared, right? Plus x plus 1 dx. Is it right? I combine like terms. That's all I did. Okay. Now then, our domain, this is calculus 1. This is calculus 1. Our domain happened to be symmetric around 0, from -1 to 1. So we learned one thing. We remind of one thing. Let me put it in red. Integral from -a to a of odd function dx. Odd functions means when you replace x by negative x, then it is negative of fx. It has symmetric with respect to origin. That's equals to 0. While if you have even function, that is 2 times integral from 0 to a of that even function. Okay. Now, in other words, if you look back here, okay, let me rewrite it this way first. Okay, integral from -1 to 1 of -3x to the 4th plus 2x squared plus 1 dx. This is for the even function plus the odd function -1 to 1 negative x cubed plus x dx. Okay, now this will be 0. Okay, while this one here is even. Is odd. This is odd, therefore it becomes 0 when you integrate that. Yeah, odd function on the symmetric domain, right? Okay, so what happened is you will get 2 times integral from 0 to 1 of negative x, I'm sorry, 3/5, negative 3/5 x to the 5th plus 2/3 x cubed plus x, actually I don't need that, from 0 to 1. Why we like 0, why we like 1 in polynomial? Because we basically just add the coefficients for 1, and for 0 it disappears. Okay, if I factor the 15, that's negative 9 plus 10 plus 15. That's 16, huh? So that's 32 over 15. Okay, so you see when I do the examples here, at the same time I reminded you about the even odd functions on the symmetric domain and how it will help us simplify our computation by big time. Okay, otherwise you will just do it long way, right? Okay, let's see the second example. Again, I take this from the book. I think our book actually explained it pretty well, but our textbook actually go over the type 1, type 2 approach thingy, which is actually useful. I mean, but I want to use the same examples to explain my technique. Okay, now we don't have the integral. They tell us that find the volume of the solid that lies under the parabola with z equals to x squared plus y squared. So this is our fxy, right? That's the integrand. Above the region D in the xy plane bounded by the line y equals to x and parabola y equals to x squared. So you have y equals to 2x. That's a line. That's a line. Y equals to 2x means the slope is 2. Let's say approximately like this. And y equals to x squared. Something looks like this. Okay, so this is y equals to 2x and y equals to x squared. Okay, now our issue is where do they intersect? So y equals to 2x equals to x squared. Do not cancel the x. No, you know from algebra you cannot do that. Okay, because x possibly 0. In fact, x is 0. Oh, that's one of the solutions. The proper way to solve this is x squared minus 2. Set one side equals to 0 and then solve by factorization. So we get x equals to 0, x equals to 2. So the domain of integration for our single integral will be 0 to 2, right? Okay, now the area D here, let me use the light color D. The area of D is integral from 0 to 2 of the top function 2x minus the bottom function x squared dx, right? Okay, if we rewrite that as double integral, that's integral from 0 to 2 of, and then integral from x squared to 2x of 1 dy dx. Are you with me? Now, if we go back to the actual integral, so the volume will be double integral over domain D of fxy dA, which when we put more details, that's integral from 0 to 2, integral from x squared to 2x of x squared plus y squared dy dx. Okay, notice that dy dx has something to do with this ordering. Okay, now let's go on. Anything from here is just calculus 1. right? Integral from 0 to 2, then x squared y plus 1/3 y cubed from x squared to 2x dx. It's integral from 0 to 2 of, what is that? 2x cubed plus 8 over 3x cubed. Am I right? Okay. Minus x to the 4th plus 1/3 x to the 6th dx. Combine like terms if possible. Integral from 0 to 2. Negative 1/3 x to the 6th minus x to the 4th plus, what is this? 14 over 3 x cubed dx. That is negative 1 over 21. So I divide further by 7. X to the 7th minus 1/5 x to the 5th plus 14 over 3 times 4, 12 x to the 4th from 0 to 2. Okay, and this is equal to what? This is 2 to the 7 is what? 32, 64, 128. 128 minus 1/5, that's 32 plus 7 over 6. I reduce that times 16. Not nice to compute. Well, anyway, negative 128 over 21 minus 32 over 5 plus 8 times 7, 56 over 3. Yeah, then you compute it from there. Okay, you compute that from there. I look at the book, I get 216 over 35. 216 over 35. Should I show you how to do that? I really quite lazy. Let's see. Let's suppose I don't know this. Let's suppose I don't know this. The LCD is what? 3 and 21 already. So it's 105. So this multiplied by 35, 56 by 35. That's a big number. Huh? Yeah, let's do 56 times 35. Now 21 times 5. So 5 times 128. And this 15 times, what's 15 times what? 21. 32, I mean 5 times 21. 32 times 21. So what I get is 56 times 35 minus 32 times 21 minus 5 times 128. Do I have a calculator to compute that? Where's my calculator? I want to see if my result is the same though. Long time not doing algebra. So 56, let me share with you my view. So I have 56 times 35 minus 32 times 21 minus 56 times 35 minus 32 times How do I delete? 2 times 21 minus 5 times 128. 648 over 105. Both of them multiple of 3, so if I reduce by 3 at the bottom, I get 35. On the top, if I reduce by 3, I get 2, 1, 6. Yeah, the same, right? Yeah, I cheat this answer from the book, by the way, and I try to match it. Okay, that's for example 2. You will see I will do more problems. Okay, I will do more problems. I hope along the way we will kind of recall how to show your work properly. Okay, and then the key part is really how to set up the double integral. That's the most difficult part. Okay, but trust me, that's okay. Okay, let's try again with example 3. Evaluate double integral over d of xy. Oh, that's very, very nice. They already tell us the integral. We just need to set up the d, huh? Okay. Y equals to x minus 1. The second part is the parabola. Y squared minus 6 over 2 equals to x. So that's y squared over 2 minus 3 equals to x. So it looks like this, huh? Right? So this is the line. Y equals to x minus 1. So let's see, where do they intersect? Solution. Y plus 1 equals to x, which is equal to y squared minus 6 over 2. So multiply both sides by 2 and set one side equals to 0. So y minus 4, y plus 2. So we have y equals to 4 and y equals to negative 2. Okay. So the y here is 4, the y here is negative 2. So our integral now will be in terms of y first, huh? So the domain D, let me change the color. So the part that I write in D's, you don't need to write down. Okay, so the area of that D is integral from negative 2 to 4 for dy of the function on the top is y plus 1. The function at the bottom is y squared over 2 minus 3. Okay, now do not combine like terms though. Do not combine like terms. You need to rewrite this into double integral right away. Integral from negative 2 to 4. Integral from y squared over 2 minus 3 to y plus 1 of dx dy. Okay, so then when we go to our double integral over d of xy dA, now we can be more specific what our d will be. It will be integral from negative 2 to 4, integral from y squared over 2 minus 3 to y minus 1 of xy dx dy. Okay, negative 2 to 4, that's 1/2 x squared y from y squared over 2 minus 3 to y minus 1 dy. Now replace that. I get integral from -2 to 4, 1/2 y, the y squared, I'm sorry, x squared, replace it by y minus 1, that's y minus 1 squared minus y squared minus 6 over 2 squared dy. I take the 1/2 out. Now I FOIL the guys inside. I simplify the guys inside. So I get y squared minus 2y plus 1 minus y to the 4th minus 12 y squared plus 36 over 4. So y times y squared minus 2y plus 1 minus 1/4 y to the 4th minus 3y squared. Actually not, it becomes plus, and then minus 9. And let's combine like terms even further. I think I will just multiply by y right away, or I get -1/4 y to the 5th, and then plus 4y cubed minus 2y squared minus 8y dy. Okay, now then from there, honestly, I'm so lazy to do this integration though, but I still want to show you. However lazy you are, just still do it. Okay, this becomes -1/24 y to the 6 plus this is y to the 4th minus 2/3 y cubed minus 4y squared from -2 to 4. Okay, and then this becomes 1/2 of, let's see, 1/24, 4 to the 6 plus 4 to the 4th minus 2/3 4 cubed minus 4 times 4 squared minus 1 to 24, -2 to the 6 plus -2 to the 4th minus 2/3 -2 cubed minus 4 times -2 squared. Painful, huh? But instead of kind of like looking at that questions and wondering what we can do, how about just do it? Okay, so this becomes what? I can cancel the 4, so that's 4 to the -4 to the 5th. What is for the 1024? 1024 over, if I reduce by 4, it will be 6 plus 4 to the 4, 16 square is 256 minus 64 times 2, 128 over 3. I'm sorry, it should be minus here. Minus 64. Okay, so then what will this be? I have -8. -8 over 3, is it right? So it's 1 over -8 times 3, that's -24, and then -2 cubed times -2 cubed. This cancels, right? Okay, and then for the second term, that's basically 2 to the 4th, that's 16, and then plus 16 over 3 minus 16. Dang, I hate doing this. Okay, that's 1/2. This is negative 512 over 3. Subtract that, that will be 2 plus 192. Is it right? Okay, minus 128 over 3. And then the last part here, 16 cancel, so I get plus 8 over 3. Okay. So this will be what? So negative 512, 128, and then 8. That's in minus 18, 146. So negative 648 over 3 plus 192. Oh. That's 1/2 times negative 200 and then 16 plus 192. What's that? 16, so that's 24. Negative 24. So the answer is negative 12. Let me check from the book. What's the answer? No, it's not negative 12. The answer is 36. Oh, shoot. Where did I compute it incorrectly? Let me look back. I see my mistake. I start from here. Duh. See, I make mistake here. It is supposed to be y plus 1. Duh. Dang. My bad. Let me fix it. I'm sorry. So plus 1 here. It should be plus 1 here. It should be plus 1 here. It should be plus here. Plus here. Okay. So that will be 2y. So it should not be plus 2y squared. So this will be plus, this will be plus, this will be plus. So this will be plus, this will be minus. So this will be plus, if that minus is 24, negative 24 over 3. Okay, so now I have negative 512 plus 128. When I subtract that, that's 14, 8, 3. Is it right? And then plus 24, that's 360. So that will give us negative 360. But that's negative 360 divided by 3 is 100, negative 120. So this will be 72. That's 36. Oh, good thing I can cheat, huh? Yeah, but you see that it's basically, it starts from this one mistake here. The sign should be y plus 1 instead of y minus 1. Thomas, if I'm the one making that kind of mistake in my test, how many points will you deduct me? 1, I think, at most 2. Out of like this question, maybe like worth 10 points. Let's say 8 points. If it is 8 points, I will deduct 1 point. If it's 10 points, I will deduct 2 points. Okay, but you need to show me the work though. Okay, you need to show me the work. Okay, so you will see that It's more about the setup, right? Instead of the computation. Okay. Yeah, if you make that mistake earlier here, if you have that y minus 1, then of course the answer you have at the end should be what I had earlier. Okay, should be what I had earlier. Well, anyway, I show you the humanity of me. As a human, I make that mistakes. But because I show my work properly, and I can easily fix it, right? Okay, that's for example 4. Example 3, let's see example 4. I think this next example is the hardest. Be very patient with that. Example 4. Find the volume. Find the volume of tetrahedron bounded by the planes x plus 2y plus c equals to 2. Let's see. So that's the plane. So this is x over 2 plus y over 1 plus c over 2 equals to 1. Okay, so in 3 dimension, the x component will be 2, the y component will be 1, the c component will be 2. So we have this plane here, and then x equals to 2y. X equals to 2y. What does it look like? It looks like this. So the intersection here, this on the ground, that's x, this is y, this is 2, this is 1. That's what it looks like, right? That's the intersection with xy plane. But y equals to x over 2. So it looks like this. This is y equals to x over 2. Bounded by z equals to 0, that's xy plane, and x equals to 0, and x equals to 0, that's yc plane. The one here. So we are dealing with actually this part. We are dealing with that part. Not this part. Not this part. Not that part. Okay. Because that part, the one Ix is bounded by y equals to 0, right? But the one bounded by x equals to 0 is the one I shaded there. So the question then, how do we develop the area D here using double integral? So you see, where do they intersect again? See, when the c equals to 0, we get x over 2 plus, you know what, why do I do that? I use this red one here just to help me getting the plane, right? The intersections with x and y and z axis. But when z equals to 0, I get x plus 2y equals to 2 and x equals to 2y. So I get 2x equals to 2x equals to 1, y equals to x equals to 1, y equals to 1/2. Okay, so the coordinate here is 1, 1/2. Now, so the setup of the integral, the volume equals to double integral from 0 to 1 for the dx. For the dy will be from lower bound, x over 2, to the upper bound, which is, what's that? So for y, x minus 2 over 2. Okay, and the height is 2 minus x minus 2y. Okay, that's the setup. Is it okay? hold on. No, it's not okay. I just realized I messed up with the order of subtraction again. That's 2 minus x over 2. Okay, I think we are ready to integrate. So this is equal to integral from 0 to 1, 2y minus xy minus y squared from x over 2 to 2 minus x over 2 dx. You know what? I think I prefer to factor that y. What I meant is this. Integral from 0 to 1, I leave it there. But then for this guy here, I use y 2 minus x minus y squared x over 2 to 2 minus x over 2 dx. Okay, you figure out yourself what is the best way to compute that. Okay, so integral from 0 to 1 of, if I replace the y, then I will get 2 minus x over 2 times 2 minus x minus 2 minus x over 2 squared, that for the first part, right? Minus the second part, x over 2 times 2 minus x squared over 4. I hope you can see the reason why I do that, especially for the first term here. You see that I have 2 minus x squared as a factor. Okay, 1/2 minus 1/4, that's 1/4. Okay, this guy, 2 minus x squared over 4 minus 2 minus x squared over 2. I'm sorry. This should be over 2 and then over 4 here. So that's how I get that 1/4. Okay, and then for the second term, I have minus x plus x squared over 2 minus x squared over 4 dx. That is integral from 0 to 1 of 2 minus x over 4, 2 minus x squared over 4, and then minus x plus x squared over 4 dx. Okay, let's compute this further. Now, of course, if you just do it long way, maybe it's simpler at this point, but I don't know. So that will be 4 minus 4x plus x squared minus 4x plus x squared over 4 dx. I do the LCD so that I can pull the LCD out 1/4. And then combine like terms on the top, I get 2x squared minus 8x plus 4. So this is 1/3 x cubed 2x squared. I factor 2 out, right? And then plus 2x from 0 to 1. Oh, the nice thing is 0 to 1, so I just add the coefficients. Okay, why do I see the answer is, where do I make mistake? Again, Thomas? Let me check my work. This should becomes plus. So this becomes 3/4. So this is 3. This becomes 4. becomes 2. This becomes 2/3. So the answer is 1/3. Okay, now that's for example 4. The good thing is we have solutions, so we can check. I mean, I take this question, these examples from the book, so I can check my work. Now, of course, then the issue when we go to our problem set, then you notice it is not that simple anymore because I don't have any way to check my final answer if I use even number. Okay, let's say for example, I do number 10. The nice thing with this number 10, they implicitly already tell us how to set up the integral. Okay, you see that you have that region D where the D is, the X is the constant. I mean, X is bounded from 1 to E, and the Y is from 0 to a function of X, right? Okay, maybe I use different color so that you can see that. Oh, if I use the green color for this will be integral from 0 to ln x dy. Now, at this point, it's then I can tell you something more. Notice that the integral, the inner integral, the one in green or lime color here, may have boundary a function of x. Okay, but the outermost integral has to be constant both ways. Okay, the inner integral may be a function of x. Now, of course, the inner integral, because you integrate it with respect to y, should not be a function of y. Okay, now then I put in my integrand, in this case is x cubed. Okay, because it is, the integrand is independent of y, I can just integrate that and give us the length of the interval, right? Now, how to integrate this? Let u equals to ln x. So du is 1 over x dx. Is that what I want to do? Well, okay, so u1 is 0, ue is 1. So what is x cubed then? So dx equals to x du, but x is e to the u. Okay, so now the integral becomes from 0 to 1. X cubed is e to the u cubed. Ln x becomes u, and dx becomes e to the u du. So this is integral from 0 to 1 u e to the 4u du. Now integration by parts. I wonder if you remember, I do tabular method. So this is equal to 1/4 e 1/4 u e to the 4u minus 1 over 16 e to the 4u from 0 to 1. When u equals to 1, that will be 1/4 e to the 4th minus 1 over 16 e to the 4th minus, when u equals to 0, it's 0 here, 1 there, minus 1 over 16. So what do we get? Factor 1/4. 3/4, that's 3 over 16e to the 4th plus 1 over 16. Okay, you know what? Let me move these. Move these here so that we have say some space. This is my red part and this is my line part. Okay, at least the way they ask this question, the domain D seems to be easy to set up. Right? Let me check my work. Now, integration by part by tabular method, I assume you can find out yourself. Otherwise, just use the regular way. Okay. I know I cannot integrate natural log of x, so I use that as a differential instead. Okay. Actually, we can do integration by parts here right away, though. This is integral from 1 to e ln x and then x cubed dx. I do derivative here, I do integral here. So this is equals to 1/4 x to the 4th ln x minus integral of 1 over x times 1 over 4 x to the 4th dx. That's from 1 to e, 1 to e. So this is 1/4 e to the 4 ln e, that's 1, minus when that's ln 1, that's 0, minus, and then this is integral from 1 to e of 1/4 x cubed dx times 1/4 x to the 4th from 1 to e. But that's 1 over 4 x e to the 4th minus 1 over 16 e minus 1. Right? I hope you see that now. This is e to the 4th here. So this is 1/4 e to the 4th minus 1 over 16 e to the 4th plus 1 over 16. We get the same thing, right? Now, I don't know which one is easier for you though. Okay, sometimes we can take long time to find out easier way to do it, but we can just use that long time to do the integral regular way. Okay, but at least from here I show you two different ways to integrate that. Seems like we cannot avoid integration by parts, huh? Okay, let me do one more problem and then I let you go. Let's find a harder question. Maybe number 26. I don't know if this is hard though. I don't know, but sometimes the question is more. Yeah, let's see this one. Enclosed by the paraboloid. Oh, this is the top, right? This is the roof. You can see this is the roof. This is the surface S, right? Given by c equals to x squared plus 3y squared. And then the planes x equals to 0, y equals to 1. X equals to 0 is y-axis. Y equals to 1. Y equals to x. And c equals to 0, that's xy plane. So it is this is the region on the ground. Okay, so the double integral, I think I will integrate it this way. So it's from 0 to 1 for the dy, and then the dx will be from 0 to y dx, right? And if you choose a y, you will start from 0 to x. Now, the actual work. So the actual work solution will be, we use that double integral from 0 to 1, 0 to y of x squared plus 3y squared dx dy. Thomas, on your integral, double integral you have above that, can I do it dy dx? Yes, if you want to use dy dx, then it will be from 0 to 1, right? But then the y will be from x to 1. In other words, you can also do this integration. This result will be the same to integral from 0 to 1, integral from x to 1 of x squared plus 3y squared dy dx. Up to you which one you want to use. Okay, but I like zeros. I prefer to use zeros. Okay, you will see it becomes very convenient when you have the boundary zeros, right? So 0 to 1, when I integrate with respect to x, that's 1/3 x cubed plus 3xy squared from 0 to y dy. You see how convenient is that when you plug in x equals to 0, right? You end up with integral from 0 to 1, 1/3 y cubed plus 3y cubed dy. That's 10/3 integral from 0 to 1 of y cubed dy. And that becomes 10/3 times 1/4 y to the 4th from 0 to 1. But that's basically 5/6. Okay, now you can try to integrate using the one on the right hand side here. You will see we're supposed to get the same result. Well, because the domain is the function, the integrand is continuous over the domain. Okay, yeah, let's do it anyway instead of just talking about it. Yeah, you know you don't like people who talks too much, right? Integral from 0 to 1. When I integrate with respect to y, I get x squared y plus y cubed from x to 1 dx. When I plug in 1 for my y, then I get x squared plus 1. And then when I plug in x for my y, I get x cubed plus x cubed dx. Combining like terms, I get x squared plus 1 minus 2x cubed dx. I will get 1/3 plus 1 minus 2/4. Yeah, it's from 0 to 1, right? But let's see, what is this? That's 1/2. Right, 1 minus 1/2 is 1/2. So 1/2 plus 1/3, that's 5/6. The same thing, huh? Okay, I think that's where I want to stop. Your suggested homework is, this section is difficult though. Okay, make sure you practice. I think the hard part is really to imagine what the solid look like, the three-dimensional solid look like in 3 dimensions. That's the hard part. Okay, so practice a lot, and again, feel free to ask me questions. I will also try to have the supplemental videos up by the time. Well, this 15.3 is not in your test too, so you don't need to worry too much about this. Okay, but I will try to also work this out before the spring break. Okay, that way then during your spring break, while you study for your test 2, you can also study ahead from these sections here. Okay, that's for today.